Namaskar. Welcome to this edition of the India Foundation podcast. This edition of the India Foundation podcast features the IF dialogue with Mr. Deep Prasad. The theme of this podcast is quantum computing, metamaterials, and artificial intelligence. Let's begin.
Good evening to Mr. Deep Prasad and to all those present. It is my pleasure to bring you a very interesting consideration on some of the most momentous developments that are taking place in science and technology today. Certain revelations have come forth which were not even suspected 20 years ago. And they modify our vision of the universe, of reality, and of ourselves. I would like to ask a young and very forward-looking, cutting-edge Indian scientist and technologist in Canada to tell us a little bit about himself and what he's doing and what he thinks the importance and the significance of it are for the world and for India as well. So, Deep, welcome. Can you please tell us a little bit about yourself from your childhood? I believe you were born in Ranchi. And how were you essentially brought into that very esoteric realm of new science and technology?
Sure. First of all, it's an honor and pleasure to be here, Come. Thank you, and thank you to the whole group for inviting me to give this talk. I was born in Ranchi in 1995 to two, very loving parents. My dad and his side, they're all IITians. He's an IITK, I think, 88 batch, and he was always a very hardcore technologist. So when we first moved, we came to the Silicon Valley, where I spent a lot of my childhood growing up and watching him in software and technology entrepreneurship. So I started getting an interest at a pretty young age as to how it works, how to build a business, how to the value of products and customers, and growing that. And then we moved to British Columbia in Canada, where he continued to work on his business. And then at this point, through and through, I was very, very interested in science, and of course, science fiction as well, as any kid would. And so somewhere along the lines, I especially got very interested in quantum mechanics, especially when I first got into it. I was 12 years old. I did not know the math. I was only interested in the philosophical implications. And then eventually university rolled around, and I ended up going to the University of Toronto for engineering. And while I was there, I kept my passion alive for tech entrepreneurship. I ended up joining the first engineering sort of hatchery that they had created. And this was an incubator for your own companies. Tried out my own sort of hardware startup while still in school. And during this entire time in university, I was constantly interested and engaged in what I would say is, I guess, intellectual, maybe distractions, since it wasn't directly related to my studies. But I kept reading up on physics, theoretical physics specifically. I built a large network of scientists and entrepreneurs around the world while I was here. And then at some point, last internship before I graduated, I was hired to be an AI, artificial intelligence engineer at the Royal Bank of Canada. That's where I got to really get my hands dirty with building and prototyping and testing artificial intelligence tools, specifically around natural language processing. And very exciting. It was a fantastic experience. And, they had given me a return offer to be leading the artificial intelligence division at wealth management in the Toronto chapter at Royal Bank of Canada. So that was a job that I ended up taking them up on for a little while. But keep in mind that in the back of my head, I was still very obsessed with theoretical physics. And I was at sort of like let's say, an existential road where I liked how high paying and stable this job was, but I wanted to work on something, I guess, much more, even more difficult, much more esoteric, as you've said. And so at this point, I had discovered a field out of just curiosity. I wondered, is there a field that intersects between two of my passions, quantum mechanics and artificial intelligence? So one day I looked up quantum artificial intelligence and I found that that it was a real field of research, and one of the and it was a subset of this overarching field called quantum computing. And so I started learning about it. And around the time that I started my job at RBC, I'd come across this opportunity at the Creative Destruction Labs, which was the world's first quantum computing incubator. So I ended up joining that incubator. And in that incubator, I got to learn a lot about quantum computing. They give you training by the world's top quantum computing scientists and the top quantum computing engineers, and they have partnerships with the first quantum computing companies in the world. So it was just diving in feet first, and I never looked back. So yeah.
Well, that's a very good background, but can you tell us, for a relatively lay audience, in not too long a sentence, what exactly can define quantum computing as opposed to the computing that we all know about? Because we have all heard in school and in university, and sometimes we have even been involved with the study of quantum mechanics. In fact, it's almost inevitable. But quantum computing, how exactly you define it? Because remember, 2 years ago, there were still papers by scientists claiming that quantum computing was an impossibility. And now we hear that the Chinese have it, the Americans have it, then you name it. So please tell us a little more about it.
Happily. In the early 1900s, starting with Max Planck, when he realized that black body radiation, when he found formulas to solve it, it was the first hints of what we call now as quantization. That at the lowest energy scales, you have what's called the quantization of energy. We used to believe that quantum states can take on a continuous range. Then fast forward 6 years later, and Einstein discovers a formula for the photoelectric effect. And that was when he officially defined this idea of quantization using Planck's constant. And of course, he won a Nobel Prize for this. Fast forward about a decade or so, really 2 decades later, and we had an entirely new field of physics known as quantum physics that described the physics of the small. The physics that you and I are used to is now called classical physics. So if I drop a pen in front of me, if I throw something against the wall or a projectile, all of these things are calculated using classical physics, which basically maps to the world of billions and trillions of atoms. The macroscopic world behaves in a way that we have an intuition for, right? Eventually, every child learns to walk and move their body and pick up an object and figure out, is this going to be heavy or not? These are all based on classical physics. However, when you look at the microscopic scale, when you look under a microscope, we see that the world of atoms follows a completely different behavior, which is quantum mechanics. So what quantum computers do is they leverage quantum physics to process information. It's purely based on quantum mechanical information processing, whereas the computers we're used to today are based on classical physics, the physics that we already have a very strong intuition for. In 1982, Richard Feynman proposed this machine. So he said a very famous line now in quantum computing, which is that nature is quantum mechanical, god damn it. So if you want to simulate it, you need a quantum mechanical machine. And so that was the day that quantum computing was born, when he published his paper, because the ability to simulate quantum mechanical systems is very, very difficult with today's computers. And after a certain size, it becomes impossible to simulate. So it became very prudent to build these quantum computing machines. Now, here's the difficult part about these machines. Any quantum mechanical system you have will collapse. There's something called wave function collapse. They will stop behaving quantum mechanically if you interfere with it. So they're highly sensitive systems. And so if you have a computer that's quantum mechanical in nature, you need to protect it from noise. You can't interfere with it. So it becomes a very difficult engineering problem. And that's why, a lot of people believe that they would never exist, especially in the late 20th century and even early 21st century. But then the first quantum computing computers came online where they started performing some basic information processes. And now we're at the stage where quantum computers are neck and neck with the world's most powerful supercomputers, where some of them are actually beating supercomputers for very specific tasks. And that was the quantum supremacy announcement by Google, where they were able to generate a random number generation pattern that would be, it would take thousands of times longer for the most powerful supercomputer to replicate. And then you have different kinds of quantum computing hardware now, different ways of making these quantum mechanical systems and computing on them. China, for example, their announcements have been around something called boson sampling. So it's using light to do computations, whereas Google's computers are using these superconducting wires. But yeah, that's where we're at right now, where we have these metaphorically small, error-prone quantum computers, but we know that they're working. And what we're very interested in now is how can we build these for useful industrial applications.
Is it then true that you can build a quantum computer that would be infinitely small in comparison with the very large supercomputers, the Crays and others that we know about?
I really love that question. So infinitely small is a relative concept, right? So eventually, we will be able to minimize the size of quantum computers. Right now, the infrastructure is very large. Often it'll take up half a room. It'll be like 10 feet by 15 feet. However, as people get better in engineering, especially with photonic implementations, eventually, and also something called nitrogen vacancy based computations, where people are looking at using diamonds and impurities that are introduced into the diamond to do quantum computations, because it takes on this quantum mechanical state and then you can affect it with laser beams. So as you shrink down those systems, you could have some of the most powerful computers just this small, right? In a diamond, in unassuming looking crystal. So eventually we will get to a point where, relatively speaking, is very small. We know that this is possible from a physics and engineering standpoint because the human body has already figured it out, right? Our cellular structures are so small, yet they're so powerful in terms of computation. So we know that there's a long way to go for minimizing the size of our quantum computers. But when we say infinite, I think of it in a literal sense. And we have a physics limit with how small anything we can build can go, which is at the Planck scale. We probe energy scales depending on how much energy you have, the smaller scale you can probe of physics. So in CERN, the scales that we're probing by colliding these particles against each other, those scales get smaller and smaller the more energy we're putting in. However, if we wanted to probe the Planck scale, the smallest possible unit we can think of space-time, the amount of energy that would need is the difference in energy between us today and the Greeks. So we're a very, very long way away from probing sub-Planck scale physics, and it's entirely unknown what happens at the truly infinite small scales.
This brings us to the fact that quantum computing could make artificial intelligence infinitely more powerful. Here I have a philosophical question for you, because as you know, there is a debate about how intelligent is artificial intelligence. In the sense, is it truly intelligence in the biological or human sense, as some scientists claim, or is it, as other researchers say, sort of a very different process, basically, which apes intelligence, but which is not truly intelligence? How do you evaluate that debate?
So it's a very prudent philosophical problem, which is there's something called the symbolic grounding problem. In artificial intelligence and computer science, the symbolic grounding problem goes like this. Every word, and you can try this at home. If you were to go on Wikipedia and you just started with a random word or definition or link that you're interested in, and you kept pressing the reference links in Wikipedia, and you just kept going from one reference page to another, eventually you would end up back to the same page that you started with. Even if it took you like 100 years, you'll get there. This is true for words too. If I started defining words like the sentence, this person is in a restaurant, and I took that sentence and I tried to give it meaning to a robot, I would have to tell the robot what the word this means. This person is what that means. This person is in a restaurant, what that means. And then I would have to define what a restaurant is. A restaurant is a building, then a building is this, and then et cetera, et cetera. And as I keep doing that, eventually I would circle back to the sentence I started with and the words I started with. So our definitions become circular, they become problematic in so doing so. So that is a symbolic grounding problem, which is how do you circumvent this circular logic in giving meanings and definitions to words? We understand that humans give meaning to everything, but how will robots ascribe meaning? Are they really understanding? Can we tell the difference between replicating knowledge and just true understanding? And right now we're at such a nascent field in philosophy that philosophers don't even agree on what it means to understand knowledge in the first place. So it becomes difficult to assess whether an artificial intelligence, even if they are very intelligent, they know a lot, it's very difficult for us to understand if they understand. And maybe they're going to be asking the same thing about us one day.
Yeah, that's extremely interesting as a reflection because it brings us back to Vedanta and Buddhist psychology and the very meaning of meaning, because again, meaning is in itself a very problematic term. Meaning can mean the use that we make of something, which gives it meaning, and it's only meaning because there is something else. Otherwise, nothing by itself means anything. So anyway, you
Absolutely. Yeah, well said. Brilliant.
It's a very interesting thing, but I suspect what's happening now is that computers are beginning, in some ways, to go ahead of us because they are not embarrassed by these existential questions. They can go literally to the heart of the matter, which sometimes leaves us completely, in a sense, in a condition of uselessness because they no longer need human beings to get what needs to be done, to do what needs to be done.
Absolutely. And, we're in for a hierarchy of intelligences because one of the things that attracted me to quantum computing was there was a lecture by Seth Lloyd. He's one of the godfathers of quantum artificial intelligence. And Seth Lloyd made a great example. He said that if you have a quantum computer generating patterns and you have a regular computer, and they're both using artificial intelligence systems to generate patterns and decode patterns, the patterns that the artificial intelligence running on a quantum computer create will be impossible to learn for the normal computer and the normal artificial intelligence trained on the computers we know today. So you'll eventually have this hierarchy of intelligence systems where, generally speaking, for many tasks, the quantum artificial intelligence will be impossible to catch up to. And so that's going to be interesting too.
I want to bring you to the topic of one of your other fields of research, which is metamaterials. Metamaterials were sometimes called ultramaterials. They have very special and bewildering properties. Can you tell us a little bit more about metamaterials?
Absolutely. In nature, imagine try to go through the following visualization. When you have rocks in a river, right? You have big enough rocks, the water goes around the rocks, and they change the path a little bit. You've obstructed their path. Now, let's say that you put up. This is the difference between a metamaterial and a natural material. Imagine if those water waves, the river, is electromagnetism of any part of the spectrum, whether it's visible light or UV or X-rays. As long as you're visualizing it like a wave. Imagine if you wanted to create very specific patterns in the river. So you sharpened the rocks, you sharpened and added 10 more rocks, and then you put them aligned in one way, or you made this intricate pattern, and now the water is moving in a very intricate pattern. That is what a metamaterial does, where it purposely directs electromagnetic radiation in a way that is useful for us, much like you would change the path of a river for your own liking. Now, metamaterials are all around us, and a metamaterial is something that is, generally speaking, unnatural. So we make very beautiful, intricate patterns to direct electromagnetic radiation. Um, one of my favorite examples is the idea of using terahertz to like terahertz frequencies and guiding those processes in metamaterials. Another very interesting thing is that actually my absolute most favorite application, which doesn't quite exist yet, is the ability to make metamaterials at macroscopic scales with negative refractive indices. So I'll unpack that. All of the objects that we see, if you have a glass of water or a coffee cup and you put a straw through the glass of water and you see how light will sort of distort the image, right? All of that is based on something called a positive refractive index, where light is bent away from the normal. If you had a negative refractive index where light bends the other way, that object becomes invisible in the Harry Potter sense, where you can no longer see what's there. And so there have been very interesting breakthroughs in negative refractive index metamaterials in the last 10 years for different parts of the electromagnetic spectrum, not for the visible part, but for things like radio waves. We can actually use negative refractive indices at nanoscales. For example, at my alma mater, University of Toronto, they were able to do this with radio waves and bend it away from the normal in the opposite direction. So there's a lot of research going into scaling these materials and making it useful for the visible spectrum. So one day we'll have technologies that are truly invisible. And I think that's very fascinating.
Yes, what one hears is that technically some metamaterials would have the property of invisibility, of indestructibility, having a memory, which means always regaining their original shape, and also being probably capable of all sorts of uses that we can't even imagine. For example, changing sizes dramatically because of their extraordinary flexibility. But are they alloys or are they actually pure substances?
They can be combination. You can have very, very complex alloy-based metamaterials. You could have something that's pure. Like, for example, the terahertz metamaterial that I was referencing, the ones that we've built, some of them are just pure graphene based, right? Just one allotrope of carbon. But you can have like a combination of germanium, for example. So it really depends. There are even like, for example, butterflies, right? There are some butterflies that have their skins, and you can consider it as a type of metamaterial where it diffracts light in a very specific way to replicate a pattern. So even nature does these things.
Now you hear about metamaterials more and more in the media because of the reports by scientists such as Dr. Eric Davis from the Texas Institute of Advanced Research, headed by some very prominent scientists. And what they're talking about are metamaterials that were actually recovered, not built, but recovered in very specific circumstances. In other words, certain craft that crashed or landed on Earth, and somehow some of these materials were preserved and are now being studied. And there was a presentation to Congress, to the US Congress, made recently by Dr. Eric Davis. So that tells us that metamaterials are actually being used somewhere by someone, and we are beginning to learn how to do that. So I know that you actually made a presentation about how to detect technosignatures of alien substances or alien life forms through quantum computing. How exactly would you explain that?
Okay, so as we, the 20th century brought us radio waves, right? Radio communication, thanks to guys like Tesla and Marconi. And all of this is based on classical physics. Our communication that we use today is not, of course, they're quantum mechanical, but they're not processing information quantum mechanically with quantum systems. What we're building today, one of the quantum adjacent technologies to quantum computers is the ability to communicate quantum information from one place to another. And here's what I mean by this. As I'm speaking to you, my voice is being conveyed using phonons, which is the sound carrier the carrier for sound. Then that gets converted into electrical energy, and that energy is brought through a wire, physically transported, transmitted to a satellite. Then it comes back to you, and then your computer is, transporting that current and then converting it to sounds, and then you can hear me. The point to note here is that you could physically take that information and physically put it through these wires and move it just like you would with water. But remember what I said about quantum mechanical systems, where the second you interfere with it, you've lost your quantum information. It's no longer behaving quantum mechanically. So if I stored information in a quantum mechanical system and I wanted to literally transport it to you, physically bring it to you, I can't do that if I can't touch it and put it through a wire. So the paradox is, how can I transmit quantum information from one place to another? Now, 40 years ago, somebody very intelligent invented, actually 50 years ago now, invented quantum teleportation protocols. So the idea is that if I took my quantum mechanical system and I entangled it with another quantum mechanical system, and I gave you one half of it, and so you kept it using very advanced engineering, you kept that quantum system safe and sound on your end. Now we have two entangled pairs of the same system. And if I took a measurement and I wanted to send you my quantum information, what I would do is purposely destroy collapse the wave function, read the classical measurements from my collapse, send it to you through classical channels, which are bounded by the speed of light. And then you would perform the right quantum unitary actions to recreate the original quantum information that I had over here in Canada. Now, that quantum information gets transported instantaneously through a medium that we don't understand. We don't know how quantum information is managed to go from one place instantaneously. But because if we want to communicate, I still have to send you classical information through a classical channel. This is why we can't exploit instantaneous quantum entanglement for communicating information, but we can use it to communicate quantum information nonetheless. And so, what my research was, my presentation to the European Astronomical Society was, let's assume that given the fact that we're developing quantum computers and quantum communication technologies, that a more advanced civilization near us would also be developing it or expecting that we will have developed it, which means that all the information that the SETI radars or any electromagnetic signals we're picking up in space, they may actually represent the classical side of quantum information. And so what I looked at was, can we use computers today that are inspired by quantum computing to use quantum inspired algorithms to figure out and search for these signals, rather than expecting that it was based on using classical computers to process them. That was what that research is about. But you mentioned Eric Davis and technosignatures. So extraterrestrial technosignatures, or so-called alien technosignatures, they don't necessarily need to come in the form of communication. A technosignature, for anyone who may not know, is a signature of that represents usage of technology by non-human civilization. So a signature could be anything even more physical. It could be a recovered, let's say, aircraft that shows up and it's a transient phenomena, that could be a techno signature as well. So when people like Eric Davis and Dr. Gary Nolan and Dr. Jacques Vallée, they do all this very interesting research in searching for physical techno signatures on Earth, where they're looking for these artifacts that could be truly alien artifacts that don't originate from man.
Yes, actually, let's face it, quantum entanglement gets rid of space-time in the sense that there is complete instantaneity. There is no longer any time lapse between emission and reception. So that's the beauty of it, because you are back to a literally Vedantic vision of the universe, in which everything is together. There is no separation. So everything is one. That's the beauty of it.
Yeah, I like that you say that, because it's conjectured that the entire universe is entangled, that truly everything is one from a physics perspective. It's a fair point.
So, what you're doing in Canada, obviously a number of other countries are racing to get to, essentially to get ahead of others. By the way, both the US government and the Chinese government have confirmed in the last few days that they are using artificial intelligence to observe, track, and analyze UFOs, now called UAPs. This is official. They have been doing it, but they are doing it better and better, which shows us something is afoot. Now, with regard to India, what is your perception of India's situation with regard to this technological advanced research? Is there, do you think India has fallen behind? Because one of my friends, Rajiv Malhotra, has conducted a number of interviews with people concerned with the subject, and his conclusion is that India is at risk of being left behind among the countries that do not master, control, or own the technology and the necessary resources for the technology. Are you able to give an assessment of that?
So when we look at the convergence of quantum computing, artificial intelligence, and unidentified aerial phenomena that the US and China and other countries are starting to study, Russia has been studying them for decades. We see that the convergence of the three lead to an exponential technological gap between countries who are investing resources and who aren't. One of those technologies alone can change the entire economic and power distribution. If you combine all three of them, it's game over. And that is exactly what countries like the US and China are doing. And so I'll address unidentified aerial phenomena a little bit more just in detail for context. We have these objects that are now confirmed by the Pentagon to be essentially capable of 5 characteristics that combined together are currently considered impossible by the known laws of physics, by general relativity, special relativity, and quantum physics. The best engineers on the planet have no idea how these unidentified aerial phenomena can fly or function in the first place. Those 5 observables, in no particular order, are hypersonic velocities with no sonic boom, transmedium travel, so the ability to go from air to water to space with no change to their external body. And the third one is instantaneous acceleration and deacceleration. When you're traveling at 33 to 88 times the speed of sound, which is how fast some of these objects fly, and they stop instantaneously, they're violating the conservation of momentum, which is a violation of the conservation of energy. And of course, that's impossible. You can't violate the conservation of energy, which means that what they're really doing is using physics that we don't understand. We use classical physics to describe these aerospace vehicles, to explain flight physics. It's all based on known physics. And so there's 2 more. One is low observability, the ability to be, for example, I have a colleague who briefed Congress on the subject on unidentified aerial phenomena. He was featured on 60 Minutes, and one of the incidences that him and his flight squadron had come up with was they were flying and their radar was registering, and under IR, the infrared spectrum, they were able to see different objects, especially their radar systems were returning that there would be massive objects in front of them. but they couldn't see anything with the naked eye. And of course, sometimes they could see these objects directly physically, but that's low observability, where you're seeing something that's, for all intents and purposes, invisible to the naked eye, yet you can still detect it with advanced sensors. And of course, that ties into the whole metamaterial discussion that I was talking about. And then the fifth one is the most peculiar. To me, it's the most mind boggling, and it has the highest potential, should it be replicated by any country, to completely change the power balance. And that is anti gravity, the ability to maintain positive lift without flight surfaces or propulsion signatures or any known propulsion system that's based on combustion. Elon Musk rockets. I'll give you an example. So I looked at a famous case that the Pentagon recently declassified. It's called the Tic Tac, the 2004 US Nimitz event. That I looked at I did the calculations for the acceleration and the velocity that it reached. Now, if you were to replicate that same acceleration velocity that it reached in US airspace above the sea level, and you wanted to use Elon Musk's SpaceX Falcon 9 rockets, you would need 6,000 of them in one place to replicate that. And it would create such a massive sonic boom, such a crazy exhaust trail. And so you have to wonder who is building these technologies. It's funny because the U.S. blames China and Russia, and they are both asking these sort of questions: who is building it, right? They're asking the U.S., they're pointing fingers, but nobody has any real answers. And so when it comes to India, what I see is immense intellectual capital. There is so much untapped potential for quantum computing, for artificial intelligence, for the study of these unidentified aerial phenomena. And I am concerned that seeing the lack of resources, both financially and intellectually, in these fields is going to leave India behind when it has no reason to. It has such smart people, right? There's no reason to. There's so many talented engineers. There's so many people who could figure out how these objects work, how to build better quantum computers and better artificial intelligence systems.
That's been my observation over the last several years. Many of the Indian scientists are very eminent in their fields, but they can be quite conservative, and they don't always want to venture where they believe no man has gone before. So that sometimes is a weakness, which comes from a fairly rigidly structured educational cursus. So this was a wonderful, very wide-ranging and incredibly precise expose. And I also want to congratulate you for your ability to give very simple examples and to make it poetic and understandable to all through vivid images. That's a rare gift. And it's wonderful in terms of pedagogy, in terms of being able to teach and get people interested, because otherwise we all know that the abstract definition of those concepts is really very hard to grasp. So illustrations and examples are very much needed, as in mythology. So on this note, I will thank you again for making yourself available from Vancouver at a very early time of the day. And I will request our fellows at India Foundation to thank you and give the vote of thanks. And of course, I also wish to thank the India Foundation for making this dialogue possible, which I'm sure will attract a lot of attention when it will be on the social media.
Thank you so much, Tom. It was an honor and pleasure. A very fun time. And thank you for all the questions.
Thank you so much for listening to this edition of the India Foundation podcast. Do like, share, and subscribe the India Foundation channel.